Hello, everyone, and welcome to our lesson on continuity. We're going to open with a three-part definition for continuity. It's really important that you understand this definition, so much so that I'm just going to tell you right now, these are the first three questions on the continuity quiz. State the three parts. So make sure that you know them exactly like they're written there, but I will explain how they work. So for continuity, the first thing is that the function has to have a value. So let's say that I told you that f of 2 is equal to 3. That means that at 2, my function's at 3. So I've chosen 2 as my c. Now the question is, does the limit as x approaches 2 exist? So remember, in order for a limit to exist, it has to be the same as it approaches from the left and the right. So let's say I've got this function and it comes down and it goes like that, and then it goes like that. The limit does exist. As I approach 2 from the left, it's coming down and it looks like it's expected to hit -1, but then there's a hole. That's okay. As I come in from the right, again, it's expected to hit -1, but there's a hole. That's okay. The limit does exist because it's the same from the left and the right, and the limit is -1. And then, well, you can see it's not continuous. That's the definition of continuity, is if the limit is equal to the actual function value, then it's continuous. So I'm going to go ahead and change this to make it continuous. I'm going to make my function value -1. And now my function is continuous. So super easy concept. It's going to be all throughout calculus. A lot of theorems rely on continuity. So we're going to go through it, but please don't overthink it. It's not meant to be that hard. So hopefully you guys learned your pre-calc well enough that you literally can just look at this and know if something's going to be continuous or not. This is a parabola. I don't even need to draw it. I don't care what it looks like. All parabolas are continuous. So if you can look at a function and say, oh, I know what that looks like, then it is continuous. This one is a rational function. It definitely has an asymptote at -3. I don't care what else happens with this graph, it is not going to be continuous. Okay, it turns out that it has an oblique asymptote, so maybe it looks like that, but it's not continuous. And hopefully at least one of you is thinking, oh, but you can simplify it. You can. This is actually not the graph. F of x is equal to x plus 3 times x minus 3 over x minus 3. It's a line. But is it continuous? No. You might remember from previous courses that there's still a hole at 3. And if you were ever wondering why we learned that, now you know. So this is the line x plus 3. So it's going to start here, and then by the time it gets to 3, it's going to be up at 6. But it still has a hole. So what we learned the other day is that it has a limit. The limit of x squared minus 9 over x minus 3 as x approaches 3 from the left or the right is 6. It does have a limit. But the function value, f of 3, is that equal to 6? No. Because you can't plug a 3 into the original equation. And that's going to be the difference between a limit and continuity. So the definition of continuity is when the limit equals the function value. The next one, again, right away, x can't be equal to -5. Whether you graph it or not, it is definitely not continuous. And then hopefully you remember this one. Sometimes you might see it like that with an extra bracket. Sometimes you might see it like this. This is how AP will write it. That's how your calculator does it. integer x. This is the greatest integer function, and it is another example of something that is definitely not continuous. Pretty much, if your pen never has to leave the paper, it's continuous. Like I said, we're not going to overthink this. Now, if you were reading this in a calculus textbook, this is the fancy way that they would say it. My job this year is going to be to write all the fancy things that your calculus book will say next year, and then give you the plain English version so that next year you're not at all overwhelmed. Continuity at a point can be summarized as follows. Interior point. A function y is equal to f of x is continuous at an interior point C of its domain if the limit as x approaches C of f of x is equal to f of C. This is literally what we just talked about. If the limit is the same as the function value, you're good to go. But then, just because they're mathematicians, they like to make everything all perfect and clear. Somebody might say, well, what if it's an endpoint? What do we do there? There's no limit from the left. It is a good point. Let's say you have f of x is equal to the square root of x minus 2. This graph looks like this. So then technically the definition doesn't work because there is no limit as you approach 2 from the left. So they accounted for this. So the second part of a continuity theorem would say a function y is equal to f of x is continuous at a left endpoint A or at a right endpoint B on the domain if the limit coming from the appropriate direction equals the function value. So obviously, as long as you're coming in from the right and you land at the function value, you're still good to go. But again, this is such an obvious topic. You would never have questioned the continuity at 2. But math textbooks are just determined to say it in the fanciest of ways. And my job this year is to help you learn those fancy ways and not be intimidated by them. There are 4 kinds of discontinuity. The first one is jump discontinuity. Go math, they gave it a nice easy name. Greatest integer function. Sometimes I don't draw it on the other side, but both sides. So they call this a jump discontinuity because literally you're traveling along and then you have to jump to the next point. Okay, sine of 1 over x. So take a minute and look that up on your graphing calculator if you want to. It's really funky looking, but I haven't figured out how to show the graphing calculator at the same time as this on my Screencastify. So I've already looked it up and I'm just going to draw it for you. But it does something like this. It's a little hard to see. And then it kind of goes up and then down. Anyway, it has this down, and then it does go back up, but on the other side. So the question then is, if you zoom in, what does it look like? It literally looks like this somehow. So it's oscillating. It doesn't ever meet. Fortunately, this is something you might see in college, so I wanted to include it here, but you are not responsible for this. If I put it on a test, I'm not going to put it on a test or a quiz, and it will not be on the AP exam. They don't include it. Number 3, infinite discontinuity. So you might know what this looks like. This is called the drum major function. Looks like that. I don't know if you can picture the drum major, their arms going up and down in that fashion. And it's called infinite discontinuity because the limit from either direction does exist and is going to infinity. So as you approach 0 from the left or the right, you do get the same limit from both sides, but obviously at 0, it doesn't actually have the answer of infinity. So it doesn't meet that first part of the definition. Our real focus for today is removable discontinuity. Removable discontinuity pretty much means there's a hole and you can fill it. So the function x squared minus 4 over x minus 2, you guys know that you can factor this. We've done this so many times in the last few days. Can be rewritten like this. But if you were to make the graph of this, you would have to graph it as a line with a hole in it, like that. So the limit as x approaches 2 from both the left and the right is 4. I can see that it reaches 4. But if I actually plugged a 2 into the equation, I don't get 4. F of 2 is not equal to 4. So how do we fix this? Super easy. We're going to make a piecewise function. So I'm going to rewrite it as f of x is equal to x squared minus 4 over x minus 2. And it's this function for x is not equal to 2. And then it's this function when x is equal to 2. This is how you could write this function. Okay? That way you've included the original function, you recognize that there's a hole, and then you've filled the hole. Or I also would accept f of x is equal to x squared minus 4 over x minus 2 for x is not equal to 2, or you could just tell me the number. And then you plug the hole with a 4 for when x is equal to 2. Both of those answers are acceptable. So in essence, you've plugged the hole, and now the function is continuous because you at 2 filled that in with a 4. Sometimes people say to me, how do I figure out what that number is? That's where limits come in. That's why we learned limits first. So you know it can't be equal to 2. You find the limit, and whatever the limit is, that's the number that you use to plug the hole. So that's what these notes say. To remove a discontinuity, define the function using a value that will make the function continuous at the point of discontinuity. This new function, which is going to be piecewise, is called the extended function. As long as the left-hand limit and right-hand limit agree and are not equal to infinity, remember that would be this case right here. As long as the left-hand limit and the right-hand limit agree and are not equal to infinity, the discontinuity can be removed. So on this one, the question is, why does this one fail continuity? You're always looking at the denominator. That's the key. X times x plus 1, if I factor that. So x can't be equal to 0, and x can't be equal to -1. And there's no fixing that. I know there's no fixing it because I can't reduce or simplify this equation. Nothing will work. If I put this over x minus 1, I can't cancel or anything. So those asymptotes aren't going anywhere. So it fails at those two spots. This next one has some hope. Let's look at it. I can take out the 4, and then I can factor the bottom, x plus 4, x minus 4, and now I can do a little canceling, but I still couldn't get rid of the discontinuity. It is still discontinuous at x is equal to -4. There's no getting around that. But you can remove the discontinuity at x is equal to +4. So sometimes you can remove part of the discontinuity, but you can't remove all of it. So that's why it fails. So your job now, if you were in school, would be to write your own piecewise functions. I would love to, tell you to stop, try these on your own. I know some of you are just going to keep watching this video, but I can't recommend enough that if you're really trying to learn this stuff, you got to just try it on your own and see if you can do it. Okay. Hopefully you're just come back from a pause. For each of the following, redefine f of x as a piecewise function to remove the discontinuity and use limits. So I'm going to factor this, x plus 3 times x minus 2 over x plus 2, x minus 2. So I can rewrite this as f of x is equal to x squared plus x minus 6 over x squared minus 4. You could write it in factored form if you want to, but I'm going to leave it like that because I thought it was a little faster to write. But here, x cannot be equal to plus or minus 2. But you can remove the discontinuity at 2. I can get rid of that. So again, the question is, what goes here? You have two choices. Some people are going to write x plus 3 over x plus 2. Or some people are going to say, well, I'm just going to plug the 2 in, which would give me 5 over 4. That is probably the more common thing to do. 5 over 4. So the limit as x approaches 2 from the left or the right of f of x is, remember, from limits. We try to plug it in. If we can't, we simplify it algebraically, and then we plug it in. So limits and continuity are intricately related. You'll see it a little better in a minute with this one, because this one's not as obvious to you, because you can't look at it and say, oh, I'm just going to factor and cancel. It's a rational function. But we can still do it. You're always going to ask yourself the same question. What can't x be? What's causing this not to be continuous? Well, x can't be 0. So this function is okay for everything except x is equal to 0. So the question you need to ask yourself is, does it have a limit? Can I get rid of this discontinuity? You can either look at the graph, you could graph it on your graphing calculator, or you could try to remember the basic concept that I taught you about this. It was one of the things you had to memorize. You memorized that sine of x over x, the limit as x approaches 0 is equal to 1. Looks like this. Okay. So I want you to really think about this. We're going to do this a lot this year. What if I called this u? Instead of x, what if I called this u, sine of u over u as u approaches 0? Meaning anything could go there. It doesn't have to be x. It could be 4x. So the limit of sine of 4x over 4x as 4x goes to 0, that is going to be equal to 1. But you might be thinking, but we don't have 4x. So we'll give it a 4x. 4x over 4. Now this piece goes to 1, and then 1 times 4 is 4. So it's going to be equal to 4 when x is equal to 0. So this is a very basic concept. It doesn't have to be x. If it's a 4x, just make the bottom a 4x. And you can do that by giving a 4 to the top and the bottom like I did here. The key is 2 steps. To write an extended function, step 1 is to write the function and the point of discontinuity, which you can see, x cannot be equal to 0. That's why we've been studying the domain for years. And then finding the limit, which hopefully you've practiced enough on, you can get that limit. Okay, the next example is on here to see if you remember how to factor 2 cubes. This is a formula that if you're in AP, you're going to have to memorize. If you are in honors, you should be adding this to your appendix. A cubed minus B cubed is A minus B times A squared plus AB plus B squared. If it's positive, A cubed plus B cubed, the formula is A plus B times A squared minus AB plus B squared. So AP, I'm sorry, there is a ton of memorization this year. So be prepared for that. Start making a list of all the things you want to memorize. So we can apply that to this situation. A is equal to X, B is equal to 1. Ignore the sign. B is not negative 1. B is just 1. And then since it's a minus, use this formula. So in other words, the formula puts the signs in for you, which is just great. A squared, A times B, X times 1, and plus B squared. Remember, B is not negative 1. Hopefully you can factor the bottom, no problem. Now I can cancel. And now I can write an extended function. The extended function can remove part of the discontinuity, but not all of the discontinuity. X cannot be equal to plus or minus 1. The best you can do for this guy is make it X is equal to positive 1 is still going to be okay. That's the one we got rid of. So if X is equal to positive 1, that's okay. We got rid of it on the top of the bottom. So how do we figure out what it is? You would do the limit as X approaches 1. I've simplified this. How do we find a limit? We substitute in when it doesn't work. We simplify algebraically and we substitute in again. 1 plus 1 plus 1 over 1 plus 1. Higher level math here. 3 halves. Okay. So that plugs one of the holes. It's an extended function. It did a little bit of good, but it wasn't completely able to do it. All right, for the next 2 examples, an error was made in trying to make the functions continuous. Find the error and fix it. Again, pause, try to do it yourself, come back. So the easiest way to do these is just to make a quick sketch. Remember that when you're looking at piecewise functions, you can be thinking about what this is. It's a line that crosses at 3. It's going to be going down. But personally, I always plot the endpoints. So I ask myself, what's happening at 2? Make an open circle. So at 2, I get 3 minus 2 is 1, open circle. So now I can picture that. And then it says at 2, it's 2. And then this is going to be a line that goes through 0 and has a shallow slope, but I need it at this endpoint. I need to know what's happening at 2. And 2 over 2 is 1, which is exactly where that one is. And it goes up 1 over 2, so it's a little more shallow than the other side. So what was the mistake? The mistake was that when somebody tried to plug the hole, they put it at 2. This should be a 1. That was the mistake. So if you didn't get that first one, then you can try the second one. Now, again, pause and try it on your own. All right, all you non-pausers, I know you're not pausing. So 1 minus x squared, you might not remember what that is. So let's talk about that for a second. It looks like something that you're not familiar with at first, but don't forget to just rearrange. It's just a parabola that's facing down and has been moved up 1. So moved up 1, and then from there, down 1 over 1, down 1 over 1. So the format's going to be different as often as I can, just to make sure that you're not, too conditioned to only learn things in a certain format. But it says when x is -1, there's a hole. So I don't know why there's a hole, but there's a little hole there. And they've made at x is equal to -1, they've made it 2. So how do you fix that hole? It should be 0. Because 0 is what you need to make it continuous. Properties of continuous functions. So sometimes you can't tell if something is continuous, but you can just look at the individual parts. So if you recognize two functions, like let's say x plus sine of x, and somebody says, is that continuous? You're thinking, I don't know what that looks like. But you know what x looks like, and you know what sine of x looks like. They're both continuous, so this is continuous. Differences, if the two differences are both, the two functions that are being subtracted are continuous, you're good. They can be multiplied. They can be multiplied by a constant. This is really the only one that's tricky. If you have a function divided by another function, the bottom has to be something that's not equal to 0, or it's not going to be continuous. And even the composition of functions. So let's say you had the square root of x plus 2. That's a composition of a square root and a linear function. So square root functions are continuous and linear functions are continuous. So this one is, even if I changed it to that. A parabola is continuous, a square root is continuous, so this is continuous. How can I make that make sense? Just in a huge example, all you have to do is look at all these parts. Absolute value is continuous, x is continuous, sine of x is continuous, this parabola is continuous. You're good. Oh, careful. It does have a denominator. Can that denominator ever be equal to 0? Is this ever equal to 0? No. Two ways to think about it. One is that it's a parabola that's been moved up 2. You know how much I love my graphs. So graphically representing it, it is never going to be equal to 0. Or you could just be thinking, no matter what number you plug in there, you're going to square it. It's positive. You add 2. You're never going to make that 0. So that's why that one is continuous. You should take a minute and write that down in your own words. So let's rewrite these. They're saying, is x plus 1 over x squared continuous? No. Again, the denominator issue. No, it is not continuous at x is equal to 0. So x is equal to 0 would be called a point of continuity. Little review of composition of functions here. This means we're going to put g in f. So f is normally something plus 1. What am I going to put in that something? X squared. X squared plus 1 is just a parabola. It is continuous. G of f of x. So g is something being squared. What's being squared? F of x. And again, that's just a parabola that's been shifted to the left 1. So yes, that's continuous. All right, your first AP level question. So this is straight from an old AP exam in the multiple choice section. Find the value for A so that the function is continuous. So personally, I would make a quick graph. It's a piecewise function. And this one starts up at 3. And it's for x is less than 2. So I do want to know what happens at 2. So I plug in a 2. 2 times 2 is 4, plus 3 is 7. 1, 2, 3, 4, 5, 6, 7. So that's another point, 2, 7. So that looks like that. For x is greater than 2, it's going to be some other line, but I want it to be continuous. So what does that mean? That means when I plug a 2 in for x, I need the answer to come out to be 7. I need my line, which I don't know what the slope is, if it's going to be steeper or shallower, but I need my line to be connected. So when I plug in a 2, I need to get 7. So 2a is equal to 6, a is equal to 3. That means I drew it completely wrong. It's steep, okay, like that. So that is the end of our continuity lesson. You do have a continuity worksheet for homework that I would make sure that you do and understand it. Have a great day, everyone.